Hello, so I did promise you all that I would try and flip the lecture, which means give lectures which you can watch on your own time and spend the class time doing problems, which I still think is a good idea, so I'm going to give it a go. So what I'm going to talk about now is using a thing called the calculus of variations to find trajectories in space which minimize or maximize some scalar quantity. Now, you've met this before, actually. You met it in second year in phy414lec2seg1, which was called classical physics, which Rhoda taught, I think, and you met it with the name Lagrangian mechanics. The reason I'm calling it calculus of variations is because I think people associate Lagrangian mechanics with the particular Lagrangian or the particular quantity you're trying to minimize, which is a thing called the action, which leads to the Lagrangian, which people usually write as the difference between the kinetic and the potential energy. And that's not the only way you can use the calculus of variations, so I wanted to be a little bit more general. But we're going to start pretty slowly by talking about small changes in quantities and how you handle small changes with ordinary calculus. And so I just want you to consider, first of all, some function f, which is a function only of a variable x. So it's a function of one variable. Now suppose you make a small change in the variable x, and we'll call that small change, which will be correspondingly small, and we'll call that change delta f. For small enough delta x, delta f is going to be equal to the derivative of f with respect to x times delta x. And you've all seen that before. Now, suppose instead we have another function p. Now that function is a function of two variables. We'll call those x and y. Now suppose you make small changes in both x and y. So we'll call them, the small changes we'll call delta x and delta y. And the question is, how much does p change overall? Well, the total change in p, which we'll call delta p, is going to be the result of first changing x by delta x, leaving y fixed, and the result of that is going to be the derivative of p with respect to x, and you write a little y down here sometimes to remind yourself that you've left y fixed, times the change in x. And then the next thing you do is you keep x fixed at its new value, and then you allow y to vary by amount delta y, and then you get another change in p, which is independent of the change resulting from the change in x, and that's given by the derivative of p with respect to y, leaving x fixed, times the change in y. And you'll notice that this looks exactly like the total derivative that we met last time. And in fact, it's exactly the same thing as the total derivative. The only thing that's changed is instead of writing dp, I've written delta p to emphasize that this is a small change in a quantity. So it's a slightly different notation in that what was written as an ordinary d before is now written as a delta, but I wouldn't worry about that. The important thing to notice notationally is that I have to write my partial derivatives with this other d where the top slopes off to the left to emphasize that p is being differentiated with respect to x, leaving the other variables, which in this case is just y, fixed, and similarly over here p is being differentiated with respect to y, leaving x fixed. So that's what partial derivatives are used for. They're reserved for functions of more than one variable. Okay, so let's do a quick example. So suppose, for example, p is actually the product of x and y. So suppose p equals xy, then the partial derivative of p with respect to x, leaving y fixed, is just y, and the partial derivative of p with respect to y, leaving x fixed, is just x. So in this case, you substitute into the equation at the bottom, and you discover that the total change in p equals y times the change in x plus x times the change in y. And notice that this bears a very strong resemblance to the ordinary product rule of differentiation, because we've basically differentiated the differential of one of these two quantities in the product is replaced by the small change, and then vice versa in the second term you've changed the other quantity, leaving the first one fixed. So this looks rather like the product rule of differentiation, which leads me to think it might be correct. Okay, now, why is this useful? Well, it's useful because it turns out that you can use this variational formula to address a particular class of problems where you have some function, and let's stick with p for a minute, some function of two variables. And let's stick with two variables, although quite obviously you could use more than two. There's no reason why you would just be able to use two variables. There could be more. And each of x and y are functions of a parameter, and I'm going to call that parameter tor. And so when does this come about? Well, it comes about when, for example, you have a curve. So if you remember last time we were talking about curves in space, right? And we had a curve that did something like this, and each point on the curve we can be described by coordinates. Let's call this x0 and y0. These are two coordinates to this particular point on this curve, right? And this is the x and y axis. I should always label my axes. And if you make each of these coordinates functions of some parameter tor, then as you vary tor, the values of x and y vary, and as the values of x and y vary, the point that the parameter tor describes moves around. So in fact, this arrangement where you have x and y both being functions of a parameter, right, and maybe there's some other quantity which is given by x and y, this is exactly the arrangement you run into in mechanics quite often. And so this particular parameter here I've written as a function of x and y of two variables, but suppose now it's actually a function of four different variables, not just x and y, but also x and the rate of change of x with respect to tor, and perhaps y, and perhaps the rate of change of y with respect to tor. Okay? Now, you might think that these two things are connected to each other, and of course they are, because one is a differential of the other. But you can think of them, for the purposes of finding the solutions to problems, as independent quantities. Okay? So now, I want you to think about what p might be. Right? And what p could be, for example, is it could be quite a complicated quantity. It could be the length of the curve. So suppose p is the length of my curve. Right? So suppose the curve starts here at point A and finishes here at point B, and somewhere in between them it does something. And in this case it does something rather general. It could also loop the loop, it could go around in circles for a while, it could go do a great big balloon thing. But, you know, suppose I want to find the curve that makes the shortest distance between A and B. Now you know what that is, of course. It's a straight line. But suppose you wanted to prove that. Suppose you wanted to start out with any curve you like and locate the curve which minimises the distances between A and B. Now, why would you want to do that? I don't know, but let's just have a go at it and see what happens. So what we're going to do is we're going to ask the question, okay, so if I allow myself to think about it for a minute, what quantity would constitute the length of the curve? Well, what it would be the sum of the lengths of all the little pieces of the curve. So let's call one of these things, one of these little segments, we'll say its length dl, right? Now, the change in that little length dl is going to correspond to the square root of the sum of dx squared and dy squared. Now these d's I guess I should write with my delta. I'm not going to do that, I'm going to use d's. It's the sum of dx squared and dy squared with the square root. Why is it that? Well, it's that because if you look at this little dl, if you magnify it, if you take a short enough section of curve, it looks straight, and that